I just want to give a small guidance of how to prepare chemistry for your entrance exams. So, if you go for chemistry, particularly chemistry is having three areas of three parts of the chemistry areas are there. One is organic chemistry, another one is inorganic chemistry and physical chemistry. So, but out of the experience I can say that generally whatever the entrance exam you are preparing, whether it is IIT JEE or Neet entrance exam or Eamcet 2014 or any other state entrance exams, generally if you are thorough with organic part and inorganic part, definitely out of 100% you can score around 75% of the marks in chemistry you can score easily. But then physical chemistry is always a deciding factor. So, if you are very well planned in physical chemistry and if you are able to thoroughly master the concepts properly, and if you are able to, with that concepts, if you are able to do the numericals confidently, then definitely your score will be 100% and you will be coming out in flying colors. So, my dear students, I am here to teach you the physical chemistry part, that is chemical kinetics. I wish you all the best for the coming entrance examination for the coming academic year. So, therefore, now we are going to start a chapter, that is chemical kinetics. If you go for chemical kinetics, a very interesting chapter, chemical kinetics. Let us put the meaning of chemical kinetics in a simple sense. The branch of chemistry which deals with the reaction rates is simply, I can say that it is chemical kinetics. Branch of chemistry dealing with reaction rates is simply nothing but chemical kinetics. But if you go for reaction rates, these reaction rates of a given reaction, reaction rates of reaction depends on, you can come to the conclusion of a given reaction rate by taking the mechanism of the reaction, one is mechanism of the reaction and the other one is factors affecting reaction rate. These are the two important components which decides the rate of reaction. So, when you are going for rate of reaction, here suppose if you are taking a stoichiometric equation, because rate of reaction is, what do you exactly mean by rate of reaction? So, rate of reaction, if you take rate of reaction, if you are taking, let it be capital R, this rate of reaction is nothing but, that is decrease in the concentration of reactants, by, that is time, is equal to increase in the concentration of products divided by time. So, here what we are able to understand here is, that means if you are taking a particular reaction, if you are taking a particular chemical reaction, say reactants gives rise to products, if you want to express in terms of rate of reaction, we can simply say rate of a reaction, that is, suppose if I am taking, if the rate of reaction, if I am taking small r instead of capital R, then rate of reaction is equal to minus of change in concentration of reactants divided by change in time is equal to plus of change in concentration of products divided by change in time. So, here at microscopic level, if the rate of reaction is instantaneous rate, so here when we are speaking about the rate of reaction instantaneous reaction, if you are taking, then the small d is going to be applicable, that is the smallest change with respect to small d, and average rate of reaction we are going to take, that is delta of the concentration of the reactants as well as concentration of the products. So, this expression small r is equal to minus of change in concentration of the reactants by change in time is equal to plus of change in concentration of the products divided by change in time is actually applicable for instantaneous reaction. So, the same rate of reaction you can also write it in the form of small r is equal to, that is minus of delta of concentration of reactant R divided by delta T is equal to plus of change in concentration of products divided by change in time. This is applicable, this expression is applicable for average rate of reaction, average rate of reaction. So that means here now we were able to derive something about the rate of reaction with respect to reactants and products, and based on this, now suppose if we take one generalized equation, suppose for example if I am taking one generalized equation, A moles of A plus B moles of B gives rise to C moles of C plus D moles of D, small d into capital D. I mean here you can take this is the stoichiometric equation, this is a general equation. To understand the rate of reaction, this is general equation. If you are taking this as general equation, that is here small a comma small b, small a comma small b are the molar coefficients of reactants, and small c comma small d are the molar coefficients of, that is, products, molar coefficients of products. So here, and here if you go for capital A and capital B, go for capital A and capital B, apart from this, going for capital A and capital B, these are the concentration of the reactants, and capital C comma capital D are the concentration of products. So however, whatever is the case, suppose again if you go back to this equation in the rate of reaction, if you are taking the rate of reaction, you are finding that we are using one negative sign with respect to reactants and we are using a positive sign with respect to products. That means it is a very clear thing, it is a very clear process that as long as the reaction progresses between reactants and products, definitely there is a decrease in the concentration of the reactants such that there is increase in the concentration of products. This minus indicates that there is a decrease in the concentration of reactants and there is an increase in the concentration of products. I mean if you plot a graph taking, if you are plotting a graph taking time on x axis and concentration of reactants, R stands for reactants, then you find that as the time progresses you find that definitely you are going to get a curve, hyperbolic curve you are going to get, and this curve itself indicates that definitely there is a decrease in the concentration of reactants as the time is progressing. Then if that is the case, if you plot the graph for products, then again take one more graph taking the concentration of, that is, products P, taking the concentration of products P, you find that here take time in the x axis and concentration of products in the y axis, then you find that as the time progresses you find that there is a increase in the concentration of products. That means from the graphs also it is very clear that as the reaction progresses from reactants to products, there is a decrease in the concentration of reactants and there is increase in the concentration of products. So if that is the case, now let us take some illustrative examples. Let us take some illustrative examples and find out how we can apply this general equation such that in the reactants the concentration is decreasing and in the products the concentration is increasing. So let us go back to the main general equation and let us try to understand how we can convert the general equation into this rate of reaction format. So if that is the case, all the molar coefficients, that is small a, small b, comma small c and small d, they are reciprocated, and with the help of reciprocation we can understand how the concentration is decreasing in the reactants and how the concentration is increasing in the products. So let me repeat the general equation, that is small a moles of A plus small b moles of B gives rise to small c moles of C plus small d moles of D. So from this general equation what we need to understand here is these two are reactants, capital A and capital B are reactants and capital C and capital D are products, P for products, R for reactants. So if you want to write this in the form of rate equation, small r is equal to all the molar coefficients, they are reciprocated, but these are reactants, so definitely there should be decrease in the concentration of the reactants. If there is a decrease in the concentration of reactants, so take the negative sign, minus of 1 by A into change in concentration of A divided by change in time is equal to again minus of 1 by B into change in concentration of B divided by change in time is equal to, that is plus of 1 by C, that means all the molar coefficients they have to be reciprocated. So, this is concentration of change in concentration of C divided by change in time is equal to plus of 1 by D into change in concentration of D divided by change in time. This is how you have to write the rate equation for the given general equation. Let us take some examples, illustrative examples. Let us take some illustrative examples. Take example 1. Suppose if I am taking N2 gas, one of the standard example, N2 gas plus H2 gas, reversible reaction, formation of ammonia through Haber's process. It is an exothermic reaction. So, 1 mole of nitrogen reacts with 3 moles of hydrogen, pure and dry nitrogen and hydrogen in their pure form. They are reacting in 1:3 ratio to give 2 moles of ammonia. So, here you are finding that 1 mole of nitrogen and 3 moles of hydrogen in the form of reactants, they are chemically reacting with each other to establish equilibrium to produce 2 moles of ammonia. So, convert this given equation, convert this chemically established equilibrium reaction into the rate equation format or rate of reaction format. So, rate of reaction small r is equal to, that is minus of change in concentration of N2 divided by change in time. Again 3 means reciprocated to minus of 1 by 3 into change in concentration of, that is hydrogen divided by change in time. So, the reactants rate expression is completed. Now, we have to go to the product side. If you are going to the product side, plus of 1 by 2 into change in concentration of ammonia divided by change in time. So, in this way you can write any kind of reaction illustratively, you can convert into rate equation. And here suppose for example, if you are taking second example, if you can take, that is N2 gas, if you can take half mole of nitrogen gas plus half mole of O2 gas, reversible reaction, we are going to take 1 mole of nitric oxide. 1 mole of nitric oxide gas is obtained. So, if that is the case, if you want to obtain the rate equation, rate of reaction is equal to, this is minus of 2 by 1, because 1 by 2 is 2 by 1 minus 2 by 1, that is into change in concentration of N2 divided by change in time is equal to, same thing repeats even in the one more reactant, that is oxygen. So, minus of 2 divided by 1 of change in concentration of O2 divided by change in time is equal to, that is equal to, again go to the product side. Product side we have nitric oxide, nitrogen monoxide, neutral oxide. So, therefore, take this nitrogen monoxide, nitric oxide, it is a product. So, therefore, change in concentration of nitric oxide divided by change in time. So, what you need to understand here is, when there is a decrease in the concentration of reactants, there is also increase in the concentration of products. If that is the case, whenever there is a decrease in the concentration of reactants, that means it is called rate of disappearance. That means with respect to, suppose for example, if I am writing an equation, if this is reactant and this is product separated by an arrow, if you take the reactants, minus of change in concentration of reactants divided by change in time is equal to plus of change in concentration of products divided by change in time. So, if that is the case, I can say that this component is rate of disappearance, and this is rate of appearance, Suppose illustratively, if you are taking in the example 1, we have minus 1 by 3 of change in concentration of H2 divided by change in time is equal to plus of 1 by 2 of change in concentration of ammonia. So, suppose if I am taking from the example 1, if this is going to become the rate of change of hydrogen R of H2, and this is going to become the rate of change of ammonia, then this I can equate it, ignoring the signs, negative and positive signs, ignoring. If you take directly rate of disappearance of hydrogen, that is 1 by 3 into rate of disappearance of hydrogen is equal to, that is 1 by 2 into rate of appearance of ammonia. So, suppose if he is asking what is the rate of disappearance with respect to appearance of ammonia, means you can take rate of disappearance of hydrogen is equal to 3/2 of rate of appearance of ammonia. Rate of appearance of ammonia. So, rate of disappearance of hydrogen is equal to 3/2 times the rate of appearance of ammonia. So, in this way we can correlate between the rate of disappearance as well as rate of appearance for the given reactions and given examples. So, you can take as many number of examples as possible. So, after this discussion, now it is a responsibility to know exactly how you can mathematically write the units for rate of reaction. Suppose if you are taking a reaction, for example, if you are taking a rate of reaction, simply rate of reaction, if you ignore the signs of the reactants as well as products concentration with respect to time, then the rate of reaction is simply represented by dC by dt. Concentration is always expressed, the concentration term is always expressed in terms of moles per liter, and the time can be expressed in minutes, seconds or hours. It all depends on what kind of unit we are trying to adopt when you are trying to solve the numerical problem. So, if rate of reaction is equal to simply dC by dt with respect to both reactants as well as products, then if you want to write the units for rate of reaction, this concentration is expressed in moles per liter into time is, you can take second as a reference. So, moles per liter into 1/second if you are going to take, then here the units are going to be moles per liter inverse of second inverse are the units for rate of reaction. So, for any rate of reaction with respect to reactants and products, these are the standard units where we can apply, that is moles per liter per second. Now, we will go for the next part of the discussion, that is factors affecting rate of reaction. We are going for the factors affecting the rate of reaction. Here there are 4 important factors. First one, nature of reactants. Let us learn one by one all the factors. So, let us have some brief discussion about the factors affecting the rate of reaction. That is, the first factor is nature of reactants. When you are going for the nature of reactants, here reactants are basically of 2 types. One is reactants involving ionic reactants. Reactants means you can take both reactants and products actually, but because the rate actually depends only on the concentration of the reactants, I mean the rate always depends only on the reactant components in general. So, that is why we are specifically mentioning reactants, nature of reactants. Nature of reactants means like ionic molecules, let me put it like this, ionic molecules, I can take ionic molecules and covalent molecules. Generally, when you are taking ionic molecules, you find that the rate of reaction in the case of ionic molecules, the rate is fast. Because in the ionic molecules there is no involvement of making and breaking of bonds. For example, if you are taking NaCl solid and when you are dissolving it in water, it becomes NaCl aqueous, no doubt about it, but NaCl aqueous, if you take, it dissociates into, that is Na plus of Cl minus, but then it will not lose its chemical identity. That means, there is no question of any breaking of bonds here. In the case of ionic molecules, we are not exactly breaking the bonds. Once the salt is dissolved in water, the salt by itself, it undergoes dissociation, it will break its lattice and spontaneously it forms ions. So, there is no such breaking and making of bonds involved in the case of ionic molecules. But if you are going for the covalent molecules, yes, there is an involvement of making and breaking of bonds. So, here in the case of covalent molecules, rate you take, rate is slow. It is slow because involvement of breaking and making of bonds. That is why the rate of reaction is slow. So, suppose let us take some examples for covalent molecules. Let us take some examples. Suppose if I am giving you A, for A if I am taking N2 gas plus O2 gas into gas plus O2 gas. I am just highlighting all the bonds over here. This is a gas, be careful, N2 plus O2 gives rise to, that is NO2. NO2 means, say I am giving you the structure like this for NO2 because nitrogen is pentavalent, it has 5 valence electrons. So, one of the electron is still there in the formation of nitrogen dioxide. So, I mean what exactly I mean to say is that N2 plus O2 gives rise to NO2 gas, say for example. If you are taking NO2, then balance the equation, take 2 over here. Yes, that means the molar coefficient is 2 here in the case of oxygen molecule. 1 mole of nitrogen is reacting with 2 moles of oxygen to give 2 moles of nitrogen dioxide. That means, if you are taking all the bonds into consideration, if you take all the bonds in the reactants and all the bonds in the products, for example, in the reactant side, here we have 3 bonds between 2 nitrogen atoms, there are 3 bonds between 2 oxygen atoms, there is a double bond means 2 bonds, 2 into 2 taken total, you take it as 4. And here in the case of nitrogen dioxide, there are 3 bonds are there, 3 into 2 6. So, you sum up everything now, 3 plus 4 plus 6, this is 10. So, total 13 bonds are involved. Keep it like this, let the rate of reaction for the first reaction be R1. Now, suppose if I am taking another reaction, say for example, I am comparing it with like H2 gas plus I2 gas gives rise to reversible reaction 2HI gas. If I am taking here between two hydrogen atoms in the hydrogen molecule, if you take hydrogen molecule, hydrogen is a single bonded covalent molecule, iodine also is a single bonded covalent molecule, and hydrogen iodide is a haloacid. So, therefore, H2 contains one single bond and also iodine contains one single bond, therefore, it gives that is 2HI. So, if you sum up all the bonds, here we have one single covalent bond, here you have one single covalent bond, and here you have 2 covalent bonds altogether. So, if you sum up, you are going to get altogether, that is 4 bonds are coming up here. So, if you compare this as rate, that is R2, it is a very clear indication that in the first case of the example, more number of bonds, more number of chemical bonds are involved. That is why definitely we can say that when you are comparing the rate of reaction for the first equation with that of second equation, you are finding that this is R2. So, you find that therefore, R1, because R1 involves more number of bonds formation, more involvement of making and breaking of bonds, that is why R1 must be less than that of R2. Lesser is the number of bonds involved, more is the rate of reaction, more the number of bonds are involved, lesser is the rate of reaction. So, that is the exact meaning of the nature of reactance with respect to rate of reaction. So, this is the first factor which we have studied in terms of factors affecting the rate of reaction. Now, we will go for the second factor. So, let us go to second factor. Second factor is, that is effect of concentration. Effect of concentration. Actually, in this effect of concentration, we are going to learn something about rate equation. We are going to discuss about the rate equation. We are going to discuss about the molecularity of reaction, and we are going to discuss about the order of reaction. So, what do you exactly mean by rate equation? In the effect of concentration, what do you exactly mean by rate equation? Rate equation actually gives the empirical relationship, the relation between the rate of reaction, rate constant, and concentration term. These three, they are empirically related in a rate equation. That is, for example, if I am taking, suppose A gives rise to products. When I say A gives rise to products, imagine that n moles of A is acting as reactants. These reactants are getting converted to products. The rate of reaction always depends upon the concentration of reactants only, but it will never depend upon the concentration of products. So, keeping this point in your mind, if you want to write the rate equation, so small r, rate of reaction, is directly proportional to concentration of A. Whatever the molar coefficient is there, that molar coefficient you can raise it to the power. When you are raising it to the power, you remove the proportionality, you are going to get a constant r is equal to that is K into concentration of A to the power of n. This is the rate equation. So, in this rate equation you are able to empirically relate between rate of reaction, rate constant, concentration term to the power of n. This power of n actually gives us the order of reaction. So, order of reaction we are going to learn in the subsequent discussion, but as of now the rate equation is empirically, in the rate equation we are trying to empirically relate between the rate of reaction, rate constant and the concentration term. So, if that is the case, in the effect of concentration, in general we can just give one generalization. As the concentration increases, in general, as concentration of reactant, as the concentration of reactants increases, rate of reaction to rate of reaction increases. So, that's it's a direct relationship. So, suppose if you take some reaction, suppose some examples, I want to continue with some examples. Suppose if I am taking A plus P gives rise to products is one reaction, I am taking the molar coefficients as 1 and 1, then so for this if I want to write the rate equation, rate of reaction is equal to rate constant into concentration of A into concentration of B, assuming that powers equal to 1 and 1, molar coefficients are 1. Sometimes if the rate of, suppose if you are taking one more reaction, 2A gives rise to products, say for example. If you are taking 2A gives rise to products, then rate is directly proportional to concentration of A. Now, the molar coefficient is 2, so that molar coefficient has to be raised to the power of 2. So, therefore, R is equal to K into concentration of A to the power of 2. So, in this way you can write whatever the number of illustrative examples you are taking, you are able to take, you can just formulate them in the form of rate equation. Suppose for example, if I am taking, say one more example if I take, so suppose some live examples if you take, decomposition of PCl5, phosphorus pentachloride. Take the phosphorus pentachloride gas, it decomposes to give PCl3 plus Cl2. So, what is the rate equation means? R is equal to K into concentration of PCl5 whole power of 1. So, that means here rate of reaction is equal to rate constant into concentration of phosphorus pentachloride to the power of 1. That means from the rate of reaction we are able to clearly relate the rate of reaction, rate constant and concentration term. Now, let us together discuss about this molecularity and the order of reaction. One basic important point between the molecularity of the reaction and order of reaction is, that is, if you go for molecularity of the reaction can be predicted theoretically or stoichiometrically we can predict the molecularity of the reaction, but if you go for order of reaction, never you can predict the order of reaction based on the stoichiometric coefficients. So, order of reaction is always determined experimentally. So, suppose if molecularity is equal to order of reaction, then that reaction we can call it as true order reaction. But there are few reactions where molecularity is not equal to order of reaction. When molecularity is not equal to order of reaction, then molecularity is not equal to, that is, order of reaction, then such condition we call it as pseudo order reaction. So, when you are going for the order of reaction, what do you exactly mean by order of reaction? Order of reaction is nothing but the sum of the powers of the concentration terms. R is equal to K into concentration of A to the power of n into concentration of B to the power of m, if I take, where n and m are the concentration powers of the concentration terms. N is the order of A and m is the order of B. It all depends what kind of values you are trying to substitute, depending upon the given data, what data you are substituting. From that you can evaluate n and m, and once you get the value of n and m, we can calculate the order of reaction. So, that means this n and m represents the order with respect to A as well as concentration of A with respect to concentration of B. N is the order of concentration term A, and m is the order of concentration term of B. So, here the order of reaction, if you are going to the order of reaction, never depends on stoichiometry of equation. It is experimentally proved, and if you go for order of reaction is basically depends on the experimental conditions. For example, some couple of examples if we discuss we will come to know. I will just put it like this. Some generalizations, if we make exceptions, I will put it like this. Exceptions, if we take, number 1, all photochemical reactions follows first order reactions. All photochemical reactions follows first order reactions. Decomposition of ammonia on surface of gold follows decomposition of ammonia on surface of gold follows zero order reaction. Inversion of cane sugar is pseudo order reaction. So, one by one if you try to follow the cases, for example, all photochemical reactions follows first order reaction means, for example, if you take decomposition of HI gas in the presence of sunlight, it follows, that is H2 gas plus I2 gas, because H mu is sunlight, H is the Planck's constant, nu is the frequency of radiation, product of Planck's constant and frequency of radiation is sunlight. So, it is sunlight photochemical reaction. So, therefore, when you write the rate for this reaction, rate of reaction is directly proportional to concentration of HI to the power of 1. So, R is equal to K into concentration of HI to the power of 1. It is a first order reaction. Similarly, if you are going for decomposition of ammonia on the surface of gold, ammonia gas, obviously when you are dissociating or decomposing ammonia upon decomposition in the presence of gold as a catalyst on the surface of gold, of course it is going to give N2 gas plus 3H2 gas. So, therefore, here rate is directly proportional to concentration of ammonia. Stoichiometrically here 2 moles are there, but because already we have generalized that decomposition of ammonia on the surface of gold follows zero order reaction. So, to the power of 0. So, R is equal to K into concentration of ammonia to the power of 0. So, R is equal to K. R is equal to K into 1 means the rate of reaction is not depending upon the concentration of the reactant. So, this is zero order reaction. Now, if you go for inversion of cane sugar, for example, third case I am just showing it up here. Cane sugar, you know that it is C12H22O11 is cane sugar. You add water in excess. When you are adding water in excess, by adding small amount of acid, acidified reaction, reversible reaction, small amount of acid, if you take, this is 2 monosaccharides, it is going to give C6H12O6 plus again C6H12 O6. So therefore, C6H12O6 plus C6H12O6, this is glucose and this is fructose. 2 monosaccharides you are going to get. But interestingly here, because we are taking water in excess, when you want to write the rate equation for the hydrolysis of cane sugar, that is reversal of cane sugar is nothing but inversion of cane sugar, means a disaccharide is giving 2 monosaccharides, that is glucose plus fructose. So here when you write the rate equation, R is equal to K into concentration of, that is C12H22O11 to the power of 1 into concentration of, that is water to the power of 0. We are taking the concentration of 0 because the water is already in excess here. It is already in excess. So if it is in excess, that means you are not taking concentration of water into consideration. So if that is the case, if you want to write the rate equation for the cane sugar, that is for this case, if you want to write the rate of reaction, so you can take this as rate is equal to K into concentration of sucrose only, C12H22O11 H22O11 to the power of 1. That means molecularity is 2 and order is 1. Number of molecules participating in the reaction are 2, definitely, because sucrose is participating and water is also participating. Sucrose is 1 molecule and water is 1 molecule. 2 molecules are participating in the reaction, but when it comes to order, we are not taking water concentration into account. So that's why we are taking concentration of water to the power of 0, concentration of water to the power of 0, concentration of cane sugar to the power of 1. So therefore the order of reaction is going to become 1 but not 2. So therefore we can say that inversion of cane sugar is definitely a pseudo order reaction. It is pseudo order reaction because molecularity is 2 and order is 1. So therefore we can say that inversion of cane sugar comes under the pseudo order reaction. Now when you go for order of reaction, when you are going for order of reaction, one more important point what we need to understand is, look at these 2 examples what I am giving you. Normally when you take, when you are taking decomposition, that is decomposition of N2O5, N2O5 upon decomposition it gives NO2 plus O2. Suppose if I take 2 over here, then if I take 4, the reaction is already balanced here. That means 2 moles of nitrogen pentoxide gas is giving nitrogen dioxide gas plus oxygen gas. But this is the overall reaction wherein which we are trying to say that 2 moles of nitrogen pentoxide is giving 4 moles of nitrogen dioxide and 1 mole of oxygen gas. But if you go for order of reaction, the order of any reaction actually depends upon the mechanism. So if you are going for mechanism of this reaction, if you take mechanism, if you take, that is taking N2O5, this N2O5 first it decomposes to give NO2 plus NO3, then again this NO3, if N2O5 is decomposing to NO2 and NO3, this is a slow step. This slow step we call it as RDS we call it as rate determining step. So here if you take the decomposition of N2O5, it is decomposing to give NO2 and NO3, nitrogen dioxide and nitrogen peroxide, it is a slow step, rate determining step. Now take the NO3 and now you again add N2O5, you are going to get, that is NO2 plus O2. So you can balance the equation. I think if you are balancing the equation, suppose if you are taking here total 5 oxygen, 5 plus 3, 8 oxygens are there. So suppose if I take 2 over here and if I take 4, 8 plus 2, 10, the reaction is, of course this is going to become the fast reaction. If you go to the mechanism, the first step is slow step, as already I told you, and second step, if you carefully observe, the nitrogen trioxide which is obtained is again in turn treated with nitrogen pentoxide. This nitrogen pentoxide reacts with nitrogen trioxide, it is a fast step and it is giving 3 moles of nitrogen dioxide and 1 mole of oxygen gas. So, suppose for example, if I am adding both these equations, this is equation 1 and this is equation 2. If I take both these reactions, if I am adding, what you are finding is like NO3 and NO3 in the reactants and products, it gets cancelled. We have N2O5 and N2O5 both are on the reactant side. So, 2N2O5 gives rise to, this is 4NO2, 3NO2 plus O2. 3NO2 plus O2 is 4NO2, 4 moles of nitrogen dioxide and 1 mole of oxygen gas. So, in the final equation it is very clear that in the final equation again we are getting 2 moles of nitrogen pentoxide. But if you take the slowest step, here we have only 1 mole of nitrogen pentoxide. Slowest step is always the step which is called rate determining step. Rate determining step is the only step which is going to decide the order of reaction. So, therefore, I am going to take the rate determining step, that is slowest step, and I am going to predict the order of reaction for this decomposition of N2O5. Virtually, if you take the overall reaction, in the overall reaction you are finding that there are 2 moles of nitrogen pentoxide which is giving 4 moles of nitrogen dioxide and 1 mole of oxygen gas. But as already I told you, order of reaction never depends upon the stoichiometry of the equation, it always depends upon the mechanism of the reaction. Order of reaction always depends on the mechanism of the reaction. So, in the mechanism, the slowest step is a very important step. So, therefore, the slowest step, if you take, rate of a reaction is directly proportional to concentration of N2O5 to the power of, because there is only 1 molar coefficient, to the power of 1 if you take. So, if you remove the proportionality, you are going to get, that is R is equal to K into concentration of N2O5 to the power of 1. That means, definitely decomposition of nitrogen pentoxide is a first order reaction, but not a second order reaction, because in the mechanism we came to know that the slow step, in the slow step only 1 mole of nitrogen pentoxide is actually getting decomposed to give nitrogen dioxide and nitrogen trioxide. So, therefore, it follows the first order reaction. Decomposition of N2O5 to give 4 moles of NO2 and 1 mole of oxygen will definitely follow. It follows first order reaction. Now, likewise, how we have studied the case 1 in the case of decomposition of nitrogen pentoxide, let us come back to the second case. Suppose, for example, you are just illustratively taking, just simply you take 2 reactants A and B. Actually, you are supposed to get the final equation as 2 moles of A gives rise to B, 2 moles of A reacts with B to give 1 mole of D. I mean, 2 moles of A and 1 mole of B are the reactants, it is giving 1 mole of D. But order of reaction never depends upon the overall reaction, it always depends upon the slowest step and one fast step. So, if we go to the slowest step, actually reactants A and B, initially 1 mole of reactant A reacts with 1 mole of reactant B to form E, which is a slow step. This is a slow step. Then once E is formed, E is acting as an intermediate. E product which is formed in the first step is acting as an intermediate. This intermediate again reacts with 1 more mole of A, because in the final equation there are 2 moles of A. 1 more mole of A reacts with the intermediate E to give a product D. So, when you are adding up both the equations, so one is slow reaction, one is fast reaction, this is equation 1 and this is equation 2. So, if you take only the slowest step in this reaction, then it is very clear that now if you want to write the order of reaction for the second case, in the second case if you want to write the order, it depends only on the slowest step. Rate of reaction is directly proportional to concentration of A into concentration of B. So, rate of reaction is equal to K into, K is the rate constant, concentration of A to the power of 1 into concentration of B to the power of 1, because if nothing is there, you can take the molar coefficient as 1 here and you can take the molar coefficient as 1 over here. So, therefore, the overall order of reaction, rate of reaction is equal to rate constant into concentration of A to the power of 1 into concentration of B to the power of 1. So, therefore, overall order, it is second order reaction. But if you take the final step after adding 2 equations, we are finding that it is actually following third order, but third order is wrong, it is only second order, because the order depends only on the slow step of the reactant molecules, but not the overall order of the reaction. However, the molecularity of the reaction is 3, but the order of reaction is 2, because molecularity is nothing but the number of molecules participating in the rate determining step. The number of molecules participating in a rate equation is nothing but the molecularity of the reaction, whereas order of reaction is nothing but the sum of the powers of the concentration terms which are involved in the rate determining step, that is lowest step is called order of reaction. Molecularity is simply nothing but the number of molecules involved in a given rate of reaction can be taken as molecularity. So, molecularity is 3 and order of reaction is 2. So, therefore, molecularity and order are differing in the case 2 also. Now, if you go for the third case, this is very interesting. Actually, if you treat this as the first equation, treat this as the first equation and treat this as second equation, first of all you try to add both the equations. When you are adding, what in the first equation, what is information we are getting in the first equation? 1 mole of chloroform, CHCl3 is chloroform, it is reacting with half mole of chlorine to give 1 mole of carbon tetrachloride and half mole of hydrogen gas. So, again take that half mole of hydrogen gas which is obtained in the first equation, again let it interact with another half mole of chlorine to give 1 mole of hydrogen chloride. So, if you add both the equations, half mole of H2 and half mole of H2, it gets cancelled. Of course, this is slow reaction and this is fast. So, therefore, here CHCl3 plus half mole of chlorine plus half mole of chlorine is 1 mole of chlorine. So, therefore, I am going to take Cl2 gives rise to, that is CCl4 plus HCl. Check out whether the reaction is actually balanced or not. Yes, in the final step the reaction is already balanced because there are 4 chlorines plus 1 chlorine, 5 chlorines. In the reactant side we have 3 chlorines and 2 chlorines. So, therefore, if this is the slowest step, if you want to write the rate equation, rate is directly proportional to concentration of the chloroform, okay, to the power of 1 into concentration of chlorine, because half mole is there here, this is 1 mole, half mole, that half mole you raise it to the power. So, what is the order of reaction for this particular reaction? What is the order of reaction means? If you remove the proportionality, you are going to get rate is equal to rate constant into concentration of chloroform to the power of 1 into concentration of chlorine to the power of half. So, 1 half, that is 1 plus half means, okay, this is 1.5. 1.5 means order can be even fractional also, it is 3 by 2. You are getting a fractional order of the reaction, because order can be fraction, order can be 0, order can even be negative, order can be first order, second order, third order, but maximum third order is the maximum order where we can learn in terms of order of reaction. So, these are one of the best examples where we can learn in understanding how the order of reaction changes along with the molecularity of the reaction. In majority of the reactions you find that molecularity is equal to order of reaction, but there are few cases where the order of reaction is never equal to molecularity of reaction. So, all the exceptions whatever we are going to get in the entrance exams, definitely all that examples I gave you, some important examples I gave you. With these examples definitely you can understand how to solve the questions, particularly based on the order and molecularity of the reactions. Now, let us go to calculation of units for nth order of reaction. If you are going for the calculation of the units for nth order of reaction, suppose for example, according to the rate equation, if you take a rate equation, you know pretty well that when you are going for the rate equation, rate is equal to rate constant into concentration of A to the power of n times. Let us take only one concentration term. With that concentration term, you multiply it with the rate constant and is equated with the rate of reaction. In fact, what you need to understand here is K is a rate constant. K is a rate constant. It depends only on nth value. Nth value means n is nothing but the order, nth order. N represents the order. As the rate of reaction increases, the rate constant value also increases. If the rate constant value increases, automatically the overall rate of reaction also increases. So, now here our aim is to write the units for the nth order of the reaction. So, if you want to write the units for nth order of reaction, assuming, let me put it like this, let this be, okay, I am just giving one equation for here, let this be equation A. So, from equation A, if you take if R is equal to K into concentration of A to the power of N. Okay. So, let the concentration term be given by C, let concentration of A be equal to C. If it is C, it should be expressed in moles per liter, should be expressed in moles per liter. So, if I am taking, and moreover let the rate of reaction be equal to dC by dt, assuming instantaneous rate of reaction is equal to dC by dt for both reactants as well as products. Ignoring the small microscopic change with respect to concentration and time, let us assume that rate is equal to C by T. So, on the LHS side I am going to substitute rate of reaction as C by T, and in the product side K into concentration, let the concentration of A given by C power of N. So, take the expression K, now obtain K, because if you know the K value then automatically the order will come. So, therefore, K is equal to C by T into 1 by C to the power of N. This is going to be equal to, that is C power of 1 minus N into T of inverse. So, concentration is already expressed in moles per liter, already I gave you the units. So, just substitute that in the concentration, let me take it as moles per liter whole inverse of 1 minus whole power of 1 minus N into time, means I am taking second inverse for our convenience. You can take second inverse, you can take minutes inverse, hours inverse, whatever the units you want to adopt, you adopt it, but depending on the numerical problem you can adopt the time unit, but as of now let us take second inverse. So, this unit again you can expand it as, that is, so here I can write this as mole of 1 minus N, mole of 1 minus N, liter of N minus 1, this you know how you got it, of second inverse. So, therefore, now if you want to calculate the units for any order, that is nth order means any order, first order, second order, 0 order, third order, whatever, this N will give you the order of reaction. So, therefore, K is equal to mole of 1 minus N, yes, mole of 1 minus N, liter of N minus 1, liter of N minus 1 of second inverse. Now, where N represents, where here continuation, where N represents nth order of reaction, where N is equal to 0, 1, 2, 3. Suppose if you are taking, for example, let us calculate if N is equal to 0, means it is 0th order, 0 order reaction. Let us write the units. So, for N is equal to 0 means take this unit, that is K is equal to, rate constant is equal to mole of 1 minus N, liter of N minus 1 of second inverse. So, take this K is equal to mole of, because it is 0 order, so 1 minus 0, 1 minus 0 is 1 only, okay, 1 minus 0 is 1, then again go for liter, that is again 1 minus 1 again 0, okay, N minus 1 na, N minus 1 means 0 minus 1 means that is liter inverse 0 minus 1. So, minus 1 of second inverse, this is the unit for, that is 0 order, unit for 0 order. So, let us go for unit of first order now. If you are going for the unit of first order, if N is equal to 1, then first order reaction, if you are taking K is equal to, just substitute the same formula here, 1 minus 1, N value is 1, 1 minus 1 0, again 1 minus 1 0. So, that means finally only second is remaining. So, I am just substituting here, that is mole of 1 minus 1, liter of again 1 minus 1 and second inverse. So, obviously unit is going to become second inverse. This is for first order reaction. So, like this you can calculate the order for second, and you can also calculate the order for the third order reaction also. Just substitute the N value. If N is 0, it is 0 order, if N is 1, it is first order, N is 2, it is second order. So, you can calculate any order based on this generalized equation. So, this nth order equation you have to keep it in your mind to calculate the order. Sometimes when you are doing the problems also in the numericals in chemical kinetics, just by looking at the unit what K value has given, With the help of that unit, you can predict what is order of reaction, and straight away we can solve the entire problem. So, units are very, very important when you are trying to handle particularly order of reactions. So, if you go for zero order reactions, here H2 gas plus I2 gas in the presence of H mu gives rise to 2HI gas. It is a photochemical reaction. Photochemical reactions. Photochemical reaction, it follows zero order. So, if you want to write the rate equation, R is directly proportional to concentration of H2 to the power of 0 into concentration of I2 to the power of 0, because photochemical reactions, in photochemical reactions the rate of reaction does not depend upon the concentration of the reactant, that we have to keep it in mind. All photochemical reactions, they follow zero order reactions. So, therefore, in this particular case, if H mu is the sunlight, it is a photochemical reaction, it is not depending upon the concentration of the reactants. So, therefore, if you remove the proportionality, R is equal to K into, that is concentration of H2 to the power of 0, concentration of I2 to the power of 0. So, K into 1, that means the rate of reaction is not at all depending upon the concentration of reactants. If the rate of reaction is not depending upon the concentration of reactants, then rate constant is equal to rate of reaction. If rate constant is equal to rate of reaction, convert this into an integrated expression for the zero order. That is, if you imagine that rate of reaction is dC by dt, then we can re-expand this as K is equal to, this change in the concentration is taken as C naught minus C divided by T. So, therefore, if you want to obtain an expression, integrated expression for the zero order reaction, for the zero order reaction, rate constant is equal to C naught minus C divided by T, where C naught is the initial concentration. Suppose if A gives rise to products, initial, its concentration is C naught, no products have been formed at time t is equal to 0 seconds. Then after final concentration out of C naught, say C amount of C moles per liter of concentration of products have been formed at t is equal to say some 5 minutes or whatever, then the remaining concentration after final it is C naught minus C is the remaining concentration. So, if that is the case, the remaining concentration after final conversion of the products, the amount of reactants remaining is nothing but C naught minus C. So, therefore, K is equal to C naught minus C is the integrated expression for zero order. Then calculation of T half for zero order. If you are calculating T half for zero order, then you can take, that is K is equal to, if T is equal to T half, then C is equal to C naught by 2, then you can take K is equal to C naught by 2K after substituting from the given equation. From the given equation, if you are substituting, rate constant is equal to C naught by 2K. So, that means this is the formula we are using, this is T half, this is T half is equal to, that is C naught by 2K, where T half is the half life for the zero order reaction, half life for zero order reaction. T half is the half life for zero order reaction. And if you want to plot the graph also, suppose if at all if you want to plot the graph for that is concentration and time, the rate constant, rate of reaction and the concentration for zero order, that is if you are plotting the graph, that is rate with respect to concentration. So, rate expressed in moles per liters per second, and this is concentration. Rate is independent of the concentration in the zero order reaction. So, therefore, you get a straight line which is parallel to x axis. That means, it is a clear indication that in zero order the rate of reaction never depends upon the concentration of the reactant. This is one graph where we can plot, and if you take this expression, that is if K is equal to C naught by C by T, so Kt is equal to C naught minus C, then you can take here, this is Kt is equal to minus C plus of C naught, we can take, or else you can just take the same expression as bring the concentration term to the RHS side, that is C naught is equal to kt plus c. If you take, then you convert this into equation of straight line, y is equal to mx plus c, where this c is the concentration term. So, this is y coordinate, this is x coordinate, and this is the slope, and intercept is there. So, if you want to plot the graph, on y axis you can take c naught concentration, on x axis you can take time, intercept is there. So, you get a straight line wherein which slope is equal to k and intercept is equal to, that is concentration term after the formation of product. C is the intercept. This is one more graph where we can plot for the zero order reaction.